Welcome to The Explainer. Today we're diving into one of humanity's biggest, boldest bets for a clean energy future, fusion power. We're going to talk about how we can recreate the very process that powers the sun, but do it right here on Earth to generate what could be nearly limitless, carbon-free electricity.
Just try to imagine it for a second. An energy source that's 1,000,000 times more dense than fossil fuels. It's a potential that offers, as this report so perfectly puts it, a path to real prosperity, all built on clean, abundant power. And look, this isn't some far-off science fiction anymore. It's the goal that scientists and now dozens of private companies are seriously racing to achieve.
Now you hear the word nuclear, and your mind probably jumps straight to traditional power plants, right? But fusion is a completely different beast. And you know, getting this difference is absolutely key to understanding its incredible potential and its very unique challenges.
So here's the bottom line. Fission, which is what powers all our current nuclear plants, works by splitting heavy atoms apart. And that process, well, it creates that long-lived radioactive waste we worry about. Fusion does the exact opposite. It takes superlight atoms, think isotopes of hydrogen, and it smashes them together. The energy release is massive, there's zero CO2 emissions, and the byproducts are only radioactive for a relatively short time. It is literally the same process that powers our sun.
Okay, so to get fusion to work, you have to create conditions that are actually hotter and under more pressure than the center of the sun. Yeah, you heard that right. We can't just replicate the sun's crazy gravity here on Earth, so we have to make up for it with even higher temperatures. And this extreme heat creates a fourth state of matter called plasma. It's this superheated, charged gas where atoms are stripped of their electrons, letting the nuclei get close enough to fuse together.
All right, so let's get into the nitty-gritty. How is a fusion power plant actually supposed to work? I mean, how do you contain a miniature star and then turn all that incredible energy into something that can actually, power your home? Well, the heart of the whole machine is the reaction chamber, and its job is to hold that plasma, a substance, remember, that is many, many times hotter than the sun. If that plasma touches the walls of the reactor, boom, it instantly cools down, the reaction stops, and you probably damage the machine. So how in the world do you hold it?
And this really shows the two main ways we're trying to do it. On one side, you have what's called magnetic confinement. This approach uses incredibly powerful magnetic fields to create a kind of invisible bottle, just holding the plasma there, suspended in space. Then on the other side, you've got inertial confinement. This is wild. It uses some of the world's most powerful lasers to just blast a tiny little fuel pellet from all sides, crushing it so fast and so intensely that fusion happens in a tiny, powerful burst.
But, no matter which method you use, the goal is to harness the energy that gets released. The fusion reaction shoots out these super high-energy neutrons. A special blanket lining the reactor wall absorbs them, and in the process, it gets incredibly hot. And from there, it's actually pretty old school. You use that heat to boil water, create steam, and spin a turbine to generate electricity. So if the basic idea is that straightforward, you got to be asking, why don't we have fusion power plants everywhere? Well, because building a star on Earth is, and I am not exaggerating, one of the hardest engineering problems humanity has ever tried to solve. Think about the materials right up next to the plasma, the stuff they call plasma-facing components. They have to survive a totally brutal environment. We are talking about heat fluxes more intense than what a spacecraft feels re-entering Earth's atmosphere. Oh, and at the same time, they're getting hammered by a constant storm of high-energy neutrons. It's just incredible.
And the challenge goes way beyond just the reactor itself. The global supply chains for all these critical parts, they're basically in their infancy. We need to figure out how to mass-produce things like high-temperature superconductors for those massive magnets, not to mention new advanced alloys that won't just crumble under all that radiation. And get this. Some of these materials are even needed to help the reactor breed its own fuel from lithium, which is a huge piece of making this whole thing self-sustaining.
But even with all these massive hurdles, the pace of innovation is really picking up. For the first time ever, we're seeing this amazing race where dozens of well-funded private companies are jumping in alongside governments and national labs, and they're all pushing for the same finish line, a commercial fusion power plant.
You can see from this timeline that we've been at this a long time. But the really key thing to focus on here is that recent shift in regulations. That decision in 2023 by the U.S. Nuclear Regulatory Commission, it has been a huge catalyst for this entire industry.
This new approach is just so important because it finally treats fusion as something fundamentally different from fission. And it is. A fusion reactor physically cannot melt down, and it doesn't create that long-lived nuclear waste. So, by regulating these things more like a particle accelerator instead of a traditional nuclear plant, it acknowledges they have a much lower risk, and that lets companies innovate faster, build prototypes quicker, which is exactly what a new technology needs to get off the ground.
So this is the ultimate question, isn't it? We have this powerful convergence of new science, a huge surge in private investment, and now a much smarter regulatory climate. Is this finally going to be enough? Are we finally going to unlock this transformative energy source, not in some distant future, but in the next decade or two, for all of us?